Hello everyone, my name is Zahra Charimova, and in this video I will walk through my solution for homework 2 for the Computer Organization and Architecture course. The goal of this assignment was to manually reverse engineer ARM hexadecimal machine code into assembly instructions. So in this video, I will explain my decoding approach, the logical structure of the program, how loops and branches are formed, and finally, the reason why the program crashes. Now, if we look at assignment for this homework, we were given 15 hexadecimal ARM instructions. And our task was to convert each instruction into its corresponding ARM assembly instruction. So we were required to decode the instructions manually, use only the methods shown in the lecture slides and explained by my professor. We should avoid any AI-assisted tools, and we should verify the final result using the ARM simulator. To recruit the assembly program, the hexadecimal instructions were first converted into binary. After that, the structure of ARM machine code for each instruction type was analyzed. For each instruction, I converted the hexadecimal value into binary and then interpreted the individual files based on the ARM instruction formats discussed in class by my professor. So let's look at number converting. As I said that I started by converting hexadecimal instruction into binary. So it's mentioned in the homework 2 document. We can convert numbers here, and if we go here, we should enter hexadecimal instruction. Let's start with this. So as we convert it, we can see binary result, and this step is crucial because ARM instructions are decoded by examining specific bit files. Here, I can clearly identify the condition file in bits 31 to 28, which tells me when the instruction executes. Bits 27 to 26 indicate the instruction class, such as data processing, memory, or branch. So, by converting the instruction into binary, I am able to separate these files and correctly decode the instruction into its assembly form. Once the instruction files are identified in binary, I can determine the exact assembly instruction, including the opcode, registers, and immediate values. And to reverse engineer the program, I first focused on identifying the type of each instruction. We know that in ARM architecture, the condition file and the instruction class give a quick idea of whatever an instruction is, data processing, memory, or branch instruction. Once the category is known to us, the remaining bits define registers, immediates, and control flags. And let's look at instruction decoding process. I will briefly explain my decoding process using one example. Let's take the instruction, as you can see on the screen, U3A01000. First, I examine bits 31 to 28, which represents the condition file. In this case, the value is 1110, which means the instruction always executes. Next, bits 27 to 26 identify the instruction class. Here, the value indicates a data processing instruction. The immediate bit is set, which tells us that the operand is an immediate value rather than a register. The opcode corresponds to a move instruction. The destination register is R1 and the immediate value is 0. So this instruction decodes to move R1 by 0, as you can see on the screen. And I use the same decoding process to all other instructions, following the instruction formats provided in the lecture slides. And loop, comparison, and branch logic. Let's talk about them. Now, I will explain the logical structure of the program. The instruction substitute R5, R3, R4. It does what? Subtract the value in R4 from R3 and stores the result in R5. More importantly, it updates the condition flags. This instruction effectively acts as a comparison between R3 and R4. After this comparison, the instruction BLT label 1 checks the condition flags and branches if the result is less than. Here, R3 is used as a loop counter and R4 contains the value 5. Inside the loop, R3 is incremented by 1 during each iteration. This creates a loop that continues executing while R3 is less than 5. Branch instructions work by modifying the program counter relative to its current value. We should emphasize that. In ARM, the effective target address is calculated using the current PC plus an offset. This offset is stored in a signed and shifted form, which allows branching both forward and backward in the program. Logically, this behavior is similar to a loop that repeats while a condition is true. The loop counter increases each iteration until the comparison condition fails, after which the program continues execution. And let's talk about branch with link and stack usage. Later in the program, a branch with link instruction is used. Where? Let's see. The BL instruction works similarly to a function call. It saves the return address in the link register, also known as LR. Immediately after that, the instruction strlr sp -4 stores the link registers on the stack. This shows that the program attempts to preserve the return address before continuing execution. And the interesting part, let's talk about reason for the crash. This section explains why the program crashes. Although the link register is saved onto the stack, it's never restored. There is no instruction such as ldr-lr-sp4 to retrieve the saved return address. And additionally, the program ends with an unconditional branch that jumps backward indefinitely. As a result, the program enters an infinite loop. Since the loop continuously pushes the values onto the stack without ever restoring them, the stack keeps growing. Eventually, the program runs out of memory, which causes a stack overflow and leads to the program crashing. So, the crash happens because the program continuously saves the link register onto the stack but never restores it. Since the program enters an infinite loop, The stack keeps growing. Eventually, this causes the simulator to exceed its memory limits, and it leads to a crash. And let's talk about splitter verification. To verify my solution, I should use the ARM splitter. So, let's check our solution. To verify my solution, I should use the ARM splitter. And if we compile our code, as you can see, compile succeed. And if we go to disassembly, we can look at opcodes. And we will see that they are same as shown in homework 2 document. Let's see here. You see E3A01000 and then E3A0200A. You see that all of them match and they are same. It's the last one. This is this. This one is this. Yes. So, I assembled the code and confirmed that the generated hexadecimal output exactly matches the provided hexadecimal dump. So, this confirms that the reverse engineered assembly code was successful. And in conclusion, what I did, I decoded the hexadecimal instructions into ARM assembly. We identified the loop, conversions, and branch logic, explained how the stack and link registers are used, and we determined the cause of the program crash, and we verified the solution using the ARM splitter. Thank you for watching, and I wish the new year is successful for all of us. Thank you.